Let's begin this video with a quick recap of what we talked about in my last lecture recording. We were talking about matrix multiplication. First of all, a matrix is just an array of numbers that has rows and columns of numbers, so it sort of looks like a table, and this is kind of how we would represent them. Matrix vector multiplication is defined like this, where if I'm trying to multiply some matrix A times some vector V, I would write it AV, and the product of this matrix vector multiplication is a vector where the entries of the vector are the dot products between the rows of the matrix and the vector. So then I did some examples of matrix vector multiplication, and of course you can go back into that recording and watch me do these examples. We talked about how if you're doing matrix vector multiplication, the number of columns of the matrix has to match exactly the number of entries in the vector. We also talked about a matrix vector equation, which is an equation that looks like this. If A and X are known, then solving for B in this matrix vector equation just means you have to do matrix vector multiplication to get that B vector. Now if A and B are known, then solving for X requires Gaussian elimination. And I showed you how really this matrix vector equation boils down to a system of linear equations. And again, solving that system of linear equations is, basically doing that whole method of what we called Gaussian elimination, which is what we did in lecture maybe 2 times ago. Next, we moved on and we were talking about matrix multiplication. And so if you have 2 matrices and you want to multiply them, then the product is itself going to be a matrix. Matrix multiplication is not commutative, so it really does matter which matrix is on the left and which matrix is on the right. And the entries in the product matrix are going to be the dot products between the rows of the left matrix and the column of the right matrix. In matrix multiplication, the number of columns in the left matrix has to be equal to the number of rows in the right matrix, otherwise it is not defined. We have a special kind of matrix called an identity matrix. The identity matrix must be a square matrix. It's the matrix with 1s on the diagonal and 0s above or below the diagonal. And the reason we call this the identity matrix is because if you multiply any vector times the identity matrix, you just get back out the same vector. And then we were talking about how some matrices are invertible, just a property of matrices. Other matrices are not invertible. So not every matrix is invertible. Now, an invertible matrix must be square, which means that some square matrices are invertible. Not every square matrix is invertible, however. You can find square matrices that are not invertible. But if you have some matrix that is not a square, then the matrix will for sure not be invertible. Now, if your matrix is invertible, then there exists an inverse matrix, which we would denote with a to the power -1, to talk about the inverse matrix. And if you multiply that matrix A times its inverse matrix, you will get as a product the identity matrix. And if you take the inverse matrix and left multiply the matrix itself, A, so you have A inverse times A, that product is also the identity matrix. So only in this very specific case, matrix multiplication becomes commutative only when you're multiplying by the inverse. But in general, remember that matrix multiplication is not commutative. So, knowing about these matrix inverses, it offers us a different solution to the matrix vector equation. My matrix vector equation is AX equals B, And now we're trying to solve for x. You remember that one way I can solve for x is by using Gaussian elimination. But what if instead I multiply both sides times the inverse matrix? Then the left side becomes just x, and then the right side of the equation becomes A inverse times B. So if I knew A inverse, then I could multiply A inverse times B. That's just matrix vector multiplication, and that would also give me the vector x. So we didn't have time to fully work examples of this, and this is the whole purpose of this video that I'm recording today. But if you wanted to find an inverse matrix, there's really two ways to do it. And I'm really only going to talk about this one because it's shorter and faster and a little bit more convenient, elegant, and so on. There's another way to do this, which you can find in almost any linear algebra textbook, but we won't get into that today because I'm not teaching a linear algebra class. Instead, we will just talk about how you can use Gaussian elimination on this kind of equation, where I have A times A inverse equals I. And just like Gaussian elimination worked before to solve our matrix vector equation, Gaussian elimination again will work on a matrix where I take the matrix A and I augment it with the identity matrix. And doing a Gaussian elimination to that augmented matrix is going to yield a matrix that is the identity matrix augmented with the inverse matrix. And that's how we're going to find these. So let's start with this first example. So I briefly talked about what that should look like last time, but we didn't actually solve it. So there, this augmented matrix is my matrix A augmented with the identity matrix. And what I'm going to try to do is I'm going to use row operations to make this first 2x2 matrix inside of my augmented matrix into the identity matrix, right? I want ones on the diagonal and zeros above and below the diagonal. So this is already 1, and that's good. I want this 3 to be a 0 now, and so I think I'll subtract 3 times the first row from the second row. I will subtract 3 times the first row from the second row, leaving the first row the same, and then 3 minus 3 times 1 is 0, 4 minus 3 times 2 is negative 2, 0 minus 3 times 1 is negative 3, and 1 minus 3 times 0 is 1. So that's my new second row after that row operation. The next thing I will want to do is make this negative 2 into a positive 1. I'm going to do that by multiplying the second row by negative 1/2. If I multiply the second row times negative 1/2, well, 0 times negative 1/2 is 0, negative 2 times negative 1/2 is 1, negative 3 times negative 1/2 is going to be 3 halves, and 1 times negative 1/2 is going to be negative 1/2. Okay? Now I want this 2 to be a 0. And to do that, I'm going to subtract 2 times the second row from the first row. And so, 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 1 minus 2 times 3 halves is negative 2. 0 minus 2 times negative half is going to be 1. Okay, and then my second row is going to remain the same. And that tells me that now I've got the identity matrix augmented with my inverse matrix, right? That's what this final matrix is here. And that tells me that my inverse matrix must be the matrix negative 2, 1, 3 halves, and negative half. I can check my work real quick by using Microsoft Excel. So I'll go ahead and do that for you. So what I'm going to do in Excel is just open up a new workbook. I'm going to type in the matrix I started with, which was 1, 2, 3, 4. Next to it, I'm going to type in the matrix that I found as the inverse, -2, 1, 3 over 2, and -1/2. And so that's what it looks like here in Excel. And I'm going to test to see if this is really the inverse matrix by doing something like this. In the formula bar, I'm going to type in equals MMULT for matrix multiplication. And then I'm going to select the first matrix, comma, the second matrix. This is what I will get if I multiply these two matrices. And of course, that resulting product matrix is 1, 0, 0, 1, which is the 2 by 2 identity matrix. And that just confirms that I did my work correctly and I actually found this matrix inverse properly. I've got one more example I want to work in this video. And it's slightly larger, so it might take a little bit more time, but we'll see how it goes. And it's saying I've got this matrix M, which is a 3 by 3 matrix. Since it's a square matrix, it could be invertible. And since I'm giving you this and asking you to find the inverse, you know, it's a good sign that it's probably invertible. Now, what I need to start off by doing is taking this matrix and augmenting it with the identity matrix. This time the 3 by 3 identity matrix. So this is my full augmented matrix, which is, again, this is M augmented with I. And I'm trying to do row operations so that now the 3 by 3 matrix on the left will be the identity matrix, and then the 3 by 3 matrix on the right should be the inverse matrix. So we'll see what happens here. I've already got 1, 0, 0, which is good. I've already got a 1 in the second, what we call the second pivot position, but I want this 1 above that to be a 0. So I'm going to take my first row and subtract the second row from the first row, and we'll see what we get. So I have 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is -1. 1 minus 0 is 1, 0 minus 1 is -1, 0 minus 0 is 0. Okay. Now, my first row is looking pretty good so far. Let's see what I would have for my second row. And I could just leave the second row the same. I'm just trying to think if there's anything I can do to speed up this process a little bit. Maybe kill 2 birds with 1 stone here so I don't have to rewrite as many matrices. And I think before I rewrite this whole second matrix, I think I'm going to subtract the third row from the second row. So my new second row is going to be the old second row minus the third row. In other words, it'll be 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0 is 1, sorry, 0, I misspoke. 1 minus 0 is 1, and 0 minus 1 is -1. Okay. Now let me copy down the third row. I will leave that as is for right now. There's one more step to get this looking like the identity matrix here on the left. And that's going to be to add the third row to the first row. So let's go ahead and add the third row to the first row, and then we'll call it a day. So 1 plus 0 is 1, 0 plus 0 is 0, -1 plus 1 is 0, 1 plus 0 is 1, -1 plus 0 is -1. 0 plus 1 is 1. Second row, I will just copy down and leave the same. And the third row, I will also just copy over and leave it the same. So now this matrix here is supposed to be I augmented with the inverse matrix. And that tells me then that my inverse matrix is this 3 by 3 matrix on the right, which is 1, -1, 1, 0, 1, -1, 0, 0, 1. And I can check my work the same way. And if this checks out in Excel, then we know that we haven't made any silly mistakes with our arithmetic, but it is always worth checking your work if you can. So, original matrix 1, 1, 0, 0, 1, 1, and 0, 0, 1. The inverse matrix is 1, negative 1, 1, 0, 1, negative 1, and 0, 1. Okay. So, here's the moment of truth. I'm going to type in equals NMULT. Then I'm going to select the first matrix, comma, select the second matrix, close parentheses, Control Shift Enter, and sure enough, this matrix product here is the 3 by 3 identity matrix, which means if this is my original matrix, the one that I started with, this is my inverse matrix, the one that we just found, and taking their product gives me this nice identity matrix. That means we did our work correctly and that this is the inverse matrix we were trying to find. Okay.